Okay, so Happy New Year, everyone, and welcome to the Tutte Colloquium today. We're very happy to have Anupan Gupta to talk today. Anupan is a professor of computer science from Carnegie Mellon University, and he works on discrete optimization, metric embeddings, approximation algorithm, and the graph algorithms. He's going to talk about the kcut problem, reading the Kager-Stein bound. So, Anupa.
Cool. Thanks, Jane. Thanks, everybody. It's a real pleasure to be at Waterloo. I wish I were there in person, but this is the next best thing. So I'll talk about some work that I did with two students, Woo-Young Lee, who's now a faculty member at U Michigan, and Jason Lee, who's just graduating. And so this is on something called the kcut problem. So I'll define it in a moment. And really, you should think of this as asking two questions. How many minimum kcuts are there, and how fast can we find them? And as always, please feel free to ask questions. I'm hoping that you'll be able to get sort of most of the technical ideas, that at least the basic ideas behind them. Okay, so what's the kcut problem? The kcut problem says, I'm given a graph G, and there are edge weights on them, and I want to delete the minimum weight edges to cut the graph into at least k components. So the to cut problem would be just the graph min cut. It's the global min cut problem. And kcut is just you want the graph to break into k connected components, at least. And think of k as being a large constant. It's k equals 2. We know this is stuff that we really know. And k being a large constant, the problem becomes interesting. More interesting, a different set of techniques, and that's the regime in which we'll be focusing today. Good. Okay. So here are two examples, and perhaps useful to keep in mind. I give you the cycle, unweighted cycle, and I ask you to break it into k pieces. What you're going to do is you're going to cut k of the edges of this. And so the optimum is k. And in fact, the number of min cuts is n choose k. You can choose any k of the edges out here. Okay. And here's the other example, canonical example. It's a complete graph. And so if you want to break this into k pieces, cutting the fewest edges, if you think about it, really what you really want to do is you want to just cut k of these, or k minus 1, really, of the vertices out. So you want to nibble away k minus 1 of the vertices. And opt now happens to be, you can do the calculation. It's really k minus 1 times the degree minus the number of edges that are going between these pieces. Those I'm double counting, so I should add them back in. And the minimum number of minimum cuts is actually n choose k minus 1. So I'm off by 1 out here. It's okay. Good. Now, one thing you'll notice is the number of minimum cuts here are more like n choose k. Okay. And so the question that we ask is, there's a computational question. How fast can we compute the k cut, the minimum k cut? And whenever I say k cut, I really mean the minimum k cut. And how many minimum k cuts are there in the graph? So these are the two questions that we'll answer, and we'll answer them simultaneously. And this goes back to this sort of the title of the talk, the Kager-Stein bound. So in fact, this is one of the sort of first works, not really one of the first works, but okay, it's an early work on the topic. And Kager and Stein gave this sort of beautiful algorithm, an extension of Kager's min-cut algorithm, that computed the minimum k cut in give or take. And I'm not really going to worry too much about constants in the exponent. The constant is there, but really you should think of this as like n to the 2k time. And it's a randomized algorithm, and I'll explain this algorithm in just a moment. And then there was a deterministic algorithm to compute this by Thorup. And then for quite some time, there was this sort of progress stalled a little because we didn't know how to do any better for k-cut. And recently, we made like a a qualitative, whatever, a slight improvement, epsilon improvement. And we showed that the answer is not like n to the 2k. It's like n to the 1.98k or something like this. And Jason in a sort of Fox best paper showed an algorithm which for unweighted graphs actually got it down to n to the k. Now, one thing I'll mention is it seems unlikely that we'll be able to do much better than n to the k runtime for computing min k-cut. And this is a reduction from k-clique. So, if we believe that k-clique should take time approximately n to the k, finding a complete graph of size k in a graph of size n, if it takes time approximately n to the k in the worst case, then it seems unlikely to do that we'll be able to do k-cut much better. And I can show you this reduction offline. It's not a big deal. It's a very simple reduction. So in your mind, you should think of as n to the k as being the goal that we are aiming towards, both for the computational question, how fast can we compute a min k-cut, and the combinatorial question, how many min k-cuts are there? Okay. And there's something known for approximations, but let's not worry about approximations. So the result that I want to tell you about today is an algorithm that finds the minimum k-cut in approximately n to the k time. There's a little bit of junk. And in fact, in sort of follow-up cleanup work, we can remove this junk. And so in fact, we can give an algorithm that computes min k-cut in n to the k time times some factor which depends only on k. So it's something like 2 to the k squared, something like that. And this algorithm also can enumerate all the minimum k-cuts in a similar amount of time. So in fact, this gives an extremal bound as well. How many minimum k-cuts are there? Good. So that's the main result of today's talk. I just want to pause for a second, see if there are any questions that people have before I proceed. Okay. So if not, let me dive right in and remind you of, yeah.
Can I just ask a quick question?
Please.
So this, I guess, is there any example that has worse than n to the n choose k as the minimum number of k-cuts? I mean, in other words, is your, okay.
So in fact, I'd be happy to conjecture that the right answer should be n choose k. I don't know how to show it. So there are these sort of still some nuisance factors floating around.
So that's tight for k equal to 2. Is there, I mean, is it even known that it's tight for k equal to 3?
Not that I know of.
Okay, thanks.
Yeah. Good. So it could be the right answer is n choose k for the number of k-cuts. It'd be very nice to prove it, very clean. For k equals 2, this is tight, as you mentioned. And in fact, the proof comes from Cargill's algorithm. So those of you who haven't seen it recently, it's one of my favorite algorithms, right? It's so the algorithm for minimum cut in a graph, just minimum 2 cut. It says pick a random edge in the graph and contract it. And here I'm assuming for the rest of this talk, let's assume unweighted graphs. We can all handle weighted graphs. Let's not worry about it. Okay? So pick a random edge in the graph and contract it. Remove self loops, keep parallel edges though. Okay, and stop when the 2 edges remain. And this is a sort of shamelessly stolen animation from Wikipedia. If I took the graph on the left and I took that bolded edge, that's the random edge I had, and I contracted it, it would give me the second graph. And then I pick this bolded edge and I contract it, and I pick this bolded edge and I contract it, and so on and so forth. And you can see, really the min cut in this graph is this one. And this is really showing us a successful run of the graph, of the algorithm. An unsuccessful run would have chosen maybe one of these edges in the middle, and then we would have, destroyed this minimum cut. Good. So this is Kargar's algorithm. And the sort of beautiful theorem that you can prove is that a minimum cut survives with probability at least 1 over n choose 2. And by the probabilistic method, this says there are at most n choose 2 minimum cuts in the graph. And the cycle shows that this is tight. And you can teach it to your first year undergrads, right? You probably do. It's good. So this is Kargar's algorithm for minimum cut. And the Kargar-Stein algorithm for minimum k cut says pick a random edge and contract it and stop when their k edges are, k vertices are remaining. And each of these super nodes that we've got now, these k super nodes, are agglomeration of these vertices. And those are the k components that we've got. Okay. And the theorem says that it's easy to extend the analysis of the previous algorithm to this one. And I'll give you a slightly cheaty analysis. I won't worry too much about the exact details, but I'll give you the analysis. So let me give you the analysis that this finds the minimum k cut with probability at least n to the minus 2k. Okay. So the algorithm says, look, suppose when r vertices remain, what's the probability of contracting an edge? What's the probability of screwing up that we contract an edge which actually belongs to the optimum cut? Okay. Well, we delete an edge from opt with probability opt over the number of edges so far, right now. Okay. And now a couple of simple bounds. The optimum is at most, one possible cut that I could have removed is I could have removed just the k minus 1 vertices of lowest degree right now. So that's an upper bound on the optimum. K minus 1 times the average of the smallest k minus 1 degrees. And the number of edges is, just by the handshake lemma, there are vertices remaining, r times the average of all r degrees divided by 2. And now you notice that the average of the smallest degrees must be smaller than the average of all degrees. So this becomes something like 2 times k minus 1 over r. And don't worry too much about the fact that r might be smaller than k, and or rather r might be smaller than 2k, and so on and so forth. Just this is an impressionistic proof. It can be made formal, but I don't want to. So this is the probability of screwing up at the rth step, that you contracted an edge which actually belonged to the cut. Okay, so the probability you don't screw up is, well, at each step you shouldn't screw up. And that is this 2 over r gives you 2 times the harmonic number. The k minus 1 remains where it is. And I'm using the approximation 1 plus x is less than e to the x, but I'm using it kind of approximately. This is about correct for, you can make this correct. Okay. And this is like n to the minus 2k. This is the Kargar-Stein analysis. Beautiful. It's one slide, right? And good. So our goal is, well, we want to improve this guy. Okay. So the question is, where is this weak? So let's look at these 2 examples right now. So in the first example, notice that the optimum divided by the number of edges. See, the thing with the cycle is, if you contract an edge in the cycle, it gives you a cycle back. So at all points, it always looks like a cycle. So now at the rth step, opt is still k, and the number of edges is r, whereas this approximation that we are using is off by a factor of 2. So this analysis seems weak. This inequality seems weak out here. We got to be careful. Okay. In the complete graph, everything seems tight. Opt is indeed k minus 1 times the smallest decrease. And the number of edges is indeed r times the average of all degrees divided by 2 at the beginning, when you have a complete graph. But as you start contracting the graph, the degrees become uneven. And that's when you start getting an advantage. The point I want to make here is that it's not clear that one of these two inequalities is always loose. Which inequality is loose kind of varies over time. So we have to be a little careful. And this is really the problem in analyzing this algorithm, in improving this algorithm. We cannot say you are weak here. The weakness changes over time. Okay. So given this, here is what we'll do. And I'll give you the proof in sort of two pieces. So I'll give you a refined analysis of this contraction algorithm. And this refined analysis will depend on a result, an extremal result, which will talk about, remember, I'm finding kcuts, but I'll give you a bound on the number of what I call medium, not too small, not too large, two cuts in the graph. I'll control the number of two cuts in order to give a result on kcuts. Okay, so more formally, and this is a quantity that I'll use throughout the rest of the talk. So maybe I'll just put a box around this. Opt is the optimal kcut value. Divided by k is this quantity z. Okay. The medium two cuts are those whose values lie between z and give or take 2z. Okay. I'll show you that the number of such medium cuts is linear. And then I'll show you that if I have only a linear number of medium cuts, then Kargerstein behaves better. Why medium cuts? The number of small cuts is vanishingly small. So actually, what I'm really doing is I'm showing you that there aren't too many small cuts in the graph, that the number of edges in the graph is more than you expect there would be. Naively. You might naively expect that average calculation that we did earlier. The number of edges is actually a little more than that. And that's where I'm going to squeeze out more. But you'll see. Okay. So for the plan for the rest of the talk is I'll, step 1, then step 2. I'm going to assume that I have a small number of medium cuts. Medium two cuts, remember. Whenever I say cuts, I really mean two cuts. I'll try to be careful about this, but if the graph has linear number of medium two cuts, then Kargerstein will behave beautifully. And then I'll show you why these two cuts are only linear. And this will be, the second part is purely set, extremal result in set systems. Good. Okay. So other questions? Otherwise, we dive in and do the first part. Okay. Good. So what am I going to do? I'm going to just analyze Kargerstein again. But I'm going to analyze it in a slightly different way. How am I going to analyze it? I'm going to have this sort of continuous viewpoint that every edge has an exponential clock with some rate, 1 over z. Z, remember, is, I don't know if, so I can't see my entire slide. Yeah, good. Z is like this opt over k. Okay, but right now it's not important what it is. It's Z. Okay. So, it basically, I think of it as just firing independently with probability some delta over z in any infinitesimal interval. Okay. So every edge I put this clock on. When the clock fires, I contract this edge. You can think of this as essentially like a distributed random, distributed version of Karger's time, because edges, these clocks will fire in random order. But now there's this advantage that, events in each time step are independent. And, as delta tends very small, only one event happens per time. Good. But events are happening more rapidly at the beginning. And I'd say it's like a firecracker, right? There has a lot of stuff happens at the beginning, and then, it slowly slows down. And you'll see why this makes our life slightly easier. Okay, so here's the standard analysis. When our vertices remain, I have at least, this is again using the definition of Z. I have R times Z over 2 edges in the graph. This is this average degree argument. Okay. So because I am contracting every edge with this probability in an infinitesimal interval of length delta, I contract so many edges times, this is the probability of contraction. This is how many edges I'm contracting in one infinite, in sort of delta time in expectation. And as delta tends to 0, the number of edges and the number of vertices being contracted are almost the same. No cycles are being contracted. And I'm waving my hands out here, and I realize that. And the formal proof handles all these things. But I want you to get the intuition. Okay. So the number of vertices was R, and it's decreasing by this much. So the new number of vertices has decreased by this factor. So after t time, the expected number of vertices is, I started off with n. I decrease in this by this much in time delta. So at time t, I have had so many epochs. And so the number of vertices looks like this. So the number of vertices started off at n. And it drops exponentially in this way. Okay, good. When will we end? We end when there's only 2 vertices or k vertices, right? So more or less we end when, this exponent out here kills this part. So at time about 2 log n. So it's looking like this. I started off at n, and I'm down to, whatever, k or 1 vertex at time 2 log n. Good. And now, and here's this sort of second thing, a fixed min cut. A min cut has so many edges. This is the probability of being contracted. So this is the probability it's not contracted. This min edge is not hit. And this happens for time t over delta again. So fixed min cut survives with this much probability. And so you're just saying, look, what is the probability that a fixed min cut survives 2 log n steps? This is n to the minus 2k. Because, you just plug in t equals 2 log n. Okay, this is the same analysis. I'm just giving you the same analysis as before. And now I can give you the sort of better analysis. And the picture is, as we were drawing earlier, it's this picture, we reach, we finish at 2 log n, and then we say, oh, the probability that min kcut survives is e to the minus kt. So this is n to the minus 2k, whatever. And actually, this picture is not the right picture I should be drawing. I should be drawing everything on a log scale. So if I look at the log of the number of vertices, it's dropping linearly. Because remember, it's an exponential drop, right? Good. So here's what I'm going to do. I'm going to argue that actually at time log n, the number of vertices is about square root n. Things will start dropping much faster. So that I'll be finished with this process at time, let's say 1.5 log n. Okay. And if this is the case, then the probability of a min cut surviving becomes something like n to the minus 1.5. Okay. Much better. And actually, this will be the first step. And of course, we'll do a much more refined analysis. But this is the main idea, right? I mean, as long as you get the main idea, the rest are details, right? So here's the idea. So I'm going to use that suppose the graph has a small number of 2 cuts, only a linear number of 2 cuts. Okay, then I'll be in great shape. Okay, why? Here's the argument. All these 2 cuts are going to just completely disappear by this mid time. Okay, so that's the argument. So the argument says any 2 cut, the probability that it survives, as long as it's of size at least z, the probability that it survives at time t is just this calculation. There's z edges, this is the probability of being contracted. So this is the probability of not being hit for so much time is e to the minus t. Okay. And there are n of these edges, n of these cuts, and they are dying with probability e to the minus t. So at log n time, they are all gone. Right? Okay. So if I write down the size of a cut, so this is the cut size. This was z. This was 2 minus epsilon z. These I said were medium cuts. At time log n, they're all gone. How many small cuts can I have? Well, the number of, see, this value has been chosen so that if you had k vertices with size smaller than z, you'd have a k cut. Right? So there are very few cuts like that. Just put them aside. So everything else is large. The degrees are large. There are a lot of edges in the graph. We are winning. And that's the main idea. So if there were only a small number of medium cuts, we win. Okay. And I'll do the calculation on the next slide, but really none of this should be a surprise to you. So suppose the graph has only a linear number of medium cuts. These medium cuts die out by time log n. There are very few vertices with small degree. So every vertex has large degree smaller than this, apart from k of these. Who cares? So after t time, the expected number of vertices is e to the minus nt over 2. This is the calculation that we did. So most vertices have large degree. There's a lot of edges. And this is exactly this behavior that we drew on the previous slide. Earlier we were drawing a picture like this, but now we'll go down at a much faster rate. Why? Because there are a lot of edges in the graph. And this stops at n to the 1.5 log n, which means already an improvement. So what's the point? Maybe let me summarize. What we said was, look, there are few cuts which have few edges. Most cuts have a lot of edges. I would love to say this right from the beginning, but I can't. There are a linear number of cuts which have at most 2z edges, but they're going to disappear pretty fast. Then the graph is denser than my previous analysis was giving. So the probability of hitting a k cut is smaller. So I'm more likely to succeed. And that's pretty much it. Okay. All this, of course, is contingent on this assumption. Suppose the graph has a small number of 2 cuts of this size. Okay. Okay. So this is what we need to prove. This is the picture again. And I gave you a bound of n to the negative 1.5k. Suppose I wanted to get down to n to the negative k, which is much faster. Of course, I shouldn't do this analysis that I did. This is a very, rough analysis that I did. I should start showing that, look, you start going down faster right from the beginning. And that's what will happen. For this, really what we do is we write down a differential equation that, tracks the number of vertices, and we show that we stay close to this differential equation bound. It's grungy. Yeah, you can read the paper if you feel like. But it's one of those things where, as somebody I heard say, if you put your mind to it, there's no way you can't prove this for yourself. Now that you know this idea, so it's just that. Good. So let's finish with the first part. I showed you if the graph has a linear number of medium cuts, then the Karger-Stein analysis is weak. Then we can do better. The algorithm is better than advertised. So now, in the remaining 20 minutes or so, I'll give you, in fact, I won't even take 20 minutes. I'll show you why the number of medium cuts is linear. So I'll prove this result. Okay, and if I lost you a little in the calculations, these calculations, Friday afternoons are is tough for me too. So this will be there will be a calculation. I'll do it, but I'll do it on the slide. So hopefully it'll be adding 2 numbers and subtracting the third. That's it. Okay. So what do I want to show? Remember, Z is opt over K. Opt is the opt K cut. And I want to show you that the number of 2 cuts in this range is linear. Okay. Formally, this is the bound that I'll show. This is not the best bound possible, but this is an easy enough bound that I'll show you. Okay. And our sanity checks for the cycle, Z, remember, is opt over K. But opt is K itself, so that's K over K, that's 1. So there's zero medium cuts. There are no cuts of size 1. And for the complete graph, you can check that only the singletons are medium cuts. So there are a linear number of cuts. So I'm not fooling you. Okay. So here are the two facts. So the first fact is, okay, so here's the thing. Think of this as the graph, and each one of those dots is the vertex. Each of these circles is one of these two cuts. What's a two cut in the graph? It's just partition like this. I'm just drawing it like a circle. And now I'm saying take these two cuts. These are all medium cuts. And just plonk them down. So the first cut was this one, the second cut was this one, and look at the vertices. And look at this like a Venn diagram, right? And suppose I put down k over 2 such two cuts. And I got k pieces in the graph. So in this case, I put down these cuts and I got 1, 2, 3, 4, 5, 6, 7, 8 pieces in the graph. If I take these components, those 8 different colored vertices form 8 different components at least, right? So if k over 2 cuts can give me k pieces, this is a k cut. With cost, how much? K over 2 times 2 minus epsilon. Less than k. Okay. So what's the moral of the story? If I take these two cuts and I put them down, they can't shatter my graph into many pieces. So I can ask the question, how large a set system can I build such that if I take any k over 2 sets from the set system and I put them down, the Venn diagram only contains k minus 1 occupied regions. It's a classic kind of question in forbidden configurations of set systems. So the first thought we had was we tried along these lines. We came up with some conjectures. We got n to the 1.98, but we got stuck. So here's the second thing. The second idea is let's use a sunflower lemma. So what's the sunflower lemma? And this is perhaps the last two slides I'll bother you with. So again, I'm thinking. So what's a sunflower? If you haven't seen this before, it's a sort of very pretty idea. It's a set system. I'm taking a set system, and I'm talking about sets of size d. Let's say exactly d. Doesn't matter. At most d. Doesn't matter. Okay. And what's a sunflower? A sunflower is a collection of sets that look like this. So if you take any two sets in your set system, in this sunflower, their intersection is this core. And it's the same core. So the intersection of any two sets in the sunflower is the same as the intersection of all the sets in the sunflower. Okay. Good. And these things are called the petals, and the petals are all disjoint from each other. So there's the core, there's the petals are disjoint. This is sunflower. And Erdős and Rado proved that if your set system is large, then it contains a large sunflower. And it's a simple proof by induction. Very nice. Actually, recent developments, Allweiss and company gave a very nice improvement of this using an information theoretic argument. Good. Okay. And there's quantitative improvement, but the important thing is qualitatively, if there's a lot of sets like this, then there's a large sunflower. Contrapositive, if there is no large sunflower, then my set system is small. Okay. And I can also ensure by losing a factor of n in the set size, in the set system size, that these sunflowers also have a non-empty core. Normally, sunflowers are allowed to have empty cores. I require non-empty cores. Okay. So my claim is, let's imagine there are no two cuts smaller than z. So remember, z is opt over k. Suppose there are no sets like this, no cuts, no two cuts like this. I want to say that the number of two cuts in this region cannot form, and this is like 2 minus epsilon z. I want to claim that the number of cuts, the collection of cuts in this region cannot form a large sunflower. Okay. So let me prove this, and that's the last thing I'll prove to you. So let's look at a sunflower. Suppose, for contradiction, I had a sunflower like this. So there's the core, and there's the petals. Okay. Now, and maybe I'll put the petals in a different color, green. Doesn't seem zoologically correct, but let's not worry about that. Okay. So let's look at the petals, and there are edges leaving this part. It's a cut, right? Remember, it's a cut in a graph. So the petals form a set. There are no cuts smaller than z. So the number of edges leaving this part is at least z. The number of edges leaving the core is at least z. But remember, this was a medium cut. So the number of edges leaving, so some of these edges could be going between the two parts. The total number of edges leaving the whole set, maybe there's a way of laser point. The number of edges leaving this part is at least z. The number of edges leaving this part is at least z. But the number of edges leaving this whole part, it's a medium cut, is smaller than 2 minus epsilon z. So how many edges go between these? Epsilon z. So epsilon z edges go from the core to the petal. Epsilon z edges go from the core to this petal, and so on and so forth. Okay. But now look at this set again. It has size at most 2 minus epsilon z. For every other petal, there's epsilon z on this, there's epsilon z on this, there's epsilon z on this, and so on and so forth. So if the total number of edges leaving this whole set is at most 2 minus epsilon, and for every other petal, I'm sending epsilon, then the number of petals is at most, well, I'll count 1 for myself, 2 minus epsilon, which is 2 minus 1 over epsilon. oh, sorry, 2 over epsilon minus 1, whatever. Let me not start getting into stupid calculations. Okay. That's it. So this says that you can't have a large sunflower. If you had a large sunflower, forget the, if you had a large sunflower, then you'd violate the calculation that we just did. So we cannot have a large sunflower. Okay. The one thing to remember is the sunflower lemma has this annoying dependence on D, the size of the set system. Our cuts could be very large. So what we have to do is we actually have to employ both the ideas together. We use both this Venn diagram idea and the sunflower idea to argue. Just put them together. The proof is not so difficult. It's a divide and conquer type argument. So let me not dwell on that. The main idea I want to tell you is that this collection of medium 2 cuts in the graph, it has a very nice set structure as a set system. It has all kinds of nice properties. You should use that. And this is what we hadn't used earlier. Once we realized we had to use this, took some time, but then we managed to get it. So, I mean, I guess for those of us who are computer scientists masquerading as discrete mathematicians, I would say it's listen to your discrete math classes. There is a lot of advantage. You never know when you'll need that lemma from your discrete math class. Okay, but anyways, that was more or less the guts of the proof. It's a slightly better analysis, well, a more careful analysis of Kargerstein. And it uses this nice sunflower lemma, which I've always wanted to use, but never had a chance until now. So, so let me wrap up. So the theorem that we saw was that the number of minimum k-cuts in the graph is something like n to the k plus order 1. And you can find it in the same amount of time as well. And here I'm assuming that k is a constant, by the way. In all these things, I'm assuming k is a constant or a large constant. I can make it go as fast as, about log n-ish, but beyond that, things are a little different. So the natural open question, put me out of my misery and tell me the correct answer for the number of minimum k-cuts of the graph is, at most n choose k. That is for the cycle. Love to know that. There's some partial progress. We've made quantitative improvements with David Harris from the University of Maryland, but still it needs at least one new idea. Get a deterministic algorithm. Despite this being like a beautiful randomized algorithm, there is some value in understanding the power of randomness. So can we get any deterministic algorithm that's better? And then finally, the results for hypergraph k-cuts are pretty wide open. I don't know. We can find them in time n to the 2k, give or take. So it's kind of like where Kargerstein was 20 years back. So can we achieve the same thing for hypergraphs? It would be nice. We need some new ideas for sure. So that's pretty much it. Thank you.
Thank you, Anupam, for this very interesting talk. So let's see if anyone in the audience wants to raise a question.
So maybe I'll ask again a quick question. So
Please.
in your first part, when you were analyzing this Karger-Stein thing using this exponential flocks,
Right.
I mean, that seemed kind of neat, but I don't know, it also introduced a bit of sort of sophistry or something. So is that kind of essential, or
No.
I mean, can we do it like the usual Karger-Stein analysis? Or?
No. So what you can do is it does introduce, you know, a seeming amount of sophistication. It's not essential. You can write down an inductive proof. It's somehow the inductive proof is not quite so sort of transparent, I feel. So you know, I thought about that and I didn't do it. But if you don't want to go this way, you can definitely write down an inductive proof and it works out just fine. It's a little more notation heavy, unfortunately, but that's partly because it's also, you know, the beauty with the inductive proofs is that it's, you know, it's all there, right? I mean, it's like a, whereas out here I was giving you the intuition for why things are working. I showed you why things were working in expectation, and then one has to make it work out actually, and then there's concentration bounds and stuff like that.
I mean, is it like the inductive proof will, I guess, give some sort of recurrence, and you still need sort of differential equations to solve that?
So you can more or less guess the form of what is the number of small cuts, or you can give bounds on the number of small cuts at every time, and then you can show this is the way it behaves in expectation. But you can control that very, very precisely in some sense. But it's kind of like magic, right? It's like, oh, I guess the form of what it should be and I tell you what it is. And it's definitely inspired by what I just said. So once we know this, we can do that.
Maybe I'll follow up with one question.
Please.
So I feel that, well, the idea is really very cool. So the intuition is that the larger cuts got killed faster, but then the smaller cuts survives longer, but hopefully you can balance the number of those and resulting in improvement. Is it possible to refine the analysis where you chunk it not like two pieces, but several chunks, and perhaps because it starts to decrease faster, you may even want the chunk size to shrink as time goes. And do you think that could potentially result in further improvement? Or in other words, if you have more bounds on the type, so not only just the median cuts, but you have various bounds for different size cuts.
So it's a very it's sort of interesting question. I was trying to recall whether I could say something meaningful about it. We did try a little bit along those lines to see if they, for various sizes of cuts, if we could control the number of cuts of that form, would it improve? What I remember is that the proofs got kind of hairy, and we soon lost track of how to handle these. But it's conceivable that those can give better analysis. So that is a very natural and very nice idea.
Okay. Any other questions? Okay. If not, let's thank Anirban again for the nice talk.
Thank you.
Sorry. Yeah, now it's the grad house time, so people just hang around and chat a little bit. So Anupan, you're welcome to just stay for the long. Oh yeah, sorry, I should stop the recording.